Good morning, everyone. Can we start?
Yes.
Okay, so today I want us to we solve a few examples on eigenvalues and eigenvectors, and then in the next class we can begin solving systems of first-order differential equations. And as you will see in the next class, they will involve these this concept of eigenvalues and eigenvectors. So straight away, start with an example. So you have your given your matrix A, so it has entries 1, -1, then 4/9, and -1/3. So what do we want to do? Question here is to find the eigenvalues and the corresponding eigenvectors. Eigenvectors of A. So, like we said the last time, we're supposed to solve the characteristic equation that is the determinant of A minus Ri. So I here is just the identity matrix is equal to 0. So I'm using R, and the notes I think they use lambda, so it doesn't really matter. It's just notation. So in this case, what will be this A minus Ri? So A minus Ri will be, this is our A, so it's -1, 4/9, then -1/3, minus R0, 0R. This, so that when we subtract those two matrices, what we get is, so you have 1 minus R, then -1, 4/9, then -1/3 minus R. And when you define the determinant, this is 1 minus R -1, 4/9, then -1/3 minus R. Is that a question? No, so okay. So this is the determinant. So this becomes determinant A minus Ri is equal to, so it's 1 minus R, then -1/3 minus R, then 4/9 times that, so it becomes plus, so it's plus 4/9. Sorry. Sorry about that. So opening the brackets, we get so 1 times -1/3 is -1/3. 1 times minus R is minus R. Then minus R times -1/3 is positive R/3. Minus R times -R is positive R squared. Then plus 4/9. So this is equal to R squared. And then we add the like term. So this is the like term. So this is minus R plus R/3. It gives us negative, is it? Negative 2 over 3 r. And 1 over 3, negative 1 over 3 plus 4 over 9 will give us, let's see. Yes, so give us 1 over 9. 1 over 9, yes. Okay. So this is our characteristic equation, and we have to equate this characteristic equation to 0 to find the eigenvalues. So r squared minus 2 over 3 r plus 1 over 9 is equal to 9. So we're supposed to find this, we can factorize. And in fact, if you look at this, this is like, you can complete the square here. So this is r squared, or let me just say this will give you r minus 1 over 3 squared is equal to 0, so that r is equal to 1 over 3 is the only eigenvalue. So in this case, the characteristic equation gives us a double root or repeated eigenvalue. So we only have one. How do we solve for the eigenvector? So to find the eigenvectors, find.
I already started one. I didn't even see the link.
Is that a question? So to find the eigenvectors corresponding to this eigenvalue, r is equal to -3. We have to solve this. So r x is equal to 0. So r here is 1 over 3. So what do we have? What we have is 1 minus 1 over 3, then minus 1, then 4 over 9, then minus 1 over 3, minus 1 over 3. Our x, which is what we want to find, we can say is x1, x2 is equal to 0, 0, the 0 vector, like this. So 1 minus 1 over 3 is 2 over 3, minus 1, then 4 over 9, and this is negative 2 over 3, x1, x2 is equal to 0, 0. And what do we get? So this is going to be 2 over 3, x1 minus x2 is equal to 0. That's the row minus column. Then the second row minus the column gives us 4 over 9 x1 minus 2 over 3 x2 is equal to 0. Then what do we notice here? Notice that these two equations are actually the same, or one is the multiple of the other, because if you multiply the second one by 3 over 2, you get exactly equation 1. So we can just work with 1. So, and so working with this one, x1 minus x2 is equal to 0. I can say my x1, if I let my x1 to be 1, it implies that my x2 will be 2 over 3. And so my vector is 1, then the second entry is 2 over 3. If I want integer entries, then I can pick on the vector, just multiplying this vector by 3. so that I get rid of the denominator and 2. So this is any of the two, any choice. There are more choices than this. I would pick on this because I just want integer entries. So I can say this vector 3, 2 is an eigenvector of the given matrix A corresponding to eigenvalue 1/3. Is this okay? We have any questions?
So at the end, the 3/2. Can you explain that again? Where did it come from?
So you're asking about 2/3 or this vector?
The 3, 2 vector.
Yes, so I said you can obtain it from this one by multiplying this one by 3. So if you multiply this vector by 3, then it's 3 times 1 is 3. 3 times 2/3 is 2. Why multiplying by 3? You just want to get integer entries. If you want, you can still work with this one. If you want integer entries, like we said last time, there are many more choices for your eigenvector. But the property is that they are all multiples of each other, should I say. You can get one from the other by multiplying by a scalar.
Okay. Thank you. Thank you.
Okay. So this is the first example. And I've seen a question in one of the messages. Let me just read it. What does it say? It says, are there instances where you would find different equations? So that is a common question. And I would say yes. In the 2x2, yes. And specific.
Hello, sir.
Yes.
Excuse me, why have you converted to 3/2 instead of just leaving it as x1 is equal to 1, x2 is equal to 2/3?
So I said I was writing it like this for the purpose of just getting integer entries. So I want x1 to be an integer, x2 to be an integer. So I just multiply this by 3 and get this. If you still leave it like this, there's no problem. It's still correct and fine. So there are many choices other than these two. There are many choices. Whichever you come up with is still fine.
And so,
yes.
I want to find out if there is a way of checking whether what you've done is correct. What's the process of the question? Long.
Oh yeah. So you can go back to your definition. You can go back to your definition of eigenvalues and eigenvectors. So what's the definition? You have to have that Ax should be equal to Rx. So R here is your eigenvalue. And X is your eigenvector. So you can check that indeed the left-hand side will equal to the right-hand side. So in this case, how do we check? So so the left-hand side is Ax. So what is our A? Our A is 1, 4/9 minus 1 minus 1/3. And what is our eigenvector? We settled for 3, 2. This was our choice. And so if If you multiply this, what you get? So it's 1 times 3, which is 3, and 1 times -2, which is 2. So it's 3 minus 2. Then 4/9 times 3 is what? It's
It's 4/3.
Thank you. And -1/3 times 2 is -2/3. Yes. So this is what you get, and it gives you 1 here for the first entry. The second entry is 2/3. Correct. Then the right-hand side. The right-hand side, you're multiplying the eigenvalue and the eigenvector. So this is the eigenvalue is 1/3. Eigenvector is 3, 2. So it's 1/3 times 3, which is 1. 1/3 times 2, which is 2/3. So yeah, this is the way to verify it. So you see that your right-hand side.
Excuse me, sir.
gives you the same.
You explain
Yeah.
on the page above. I remain behind.
Which one?
Sorry. The network glitched, so I didn't really get the page right above.
So on this page, is it?
Yes, it is.
So here we're just trying to find the eigenvectors corresponding to the eigenvalue 1/3. So it's the usual. You have to solve this equation. You're solving for x. So A minus Ri is this matrix. This is your x. You catch 2 equations. They usually turn out to be the same. You just work with 1. So working with 1, you get yes, this is the equation you work with. So you get your x1 and x2, which gives you this as one of your solutions and this as your other solution. So you can choose whichever vector you want to work with. In this case, I chose this one. And so I say this vector is an eigenvector of corresponding to eigenvalue 1/3. Is that okay?
Yes, it is okay. Thank you.
And on this page, we're just verifying that what we did was correct. So we go back to the definition of eigenvalue and eigenvector. We check that this equation will be satisfied by our choices of x and r at the eigenvalue. So indeed, the left-hand side was equal to the right-hand side. So what we did is indeed correct. Can we move on?
Just a bit. Okay, we can move on now. Thank you.
Okay. So there was a question which was talking about those 2 equations we get when we are solving for eigenvectors. Are they always the same? So to answer that question, I would prefer we do this example. So let's consider this. Let's consider this this matrix. So it has entry 2, 0, and 0, 2. So the task again is to find eigenvalues and eigenvectors. So find eigenvalues and eigenvectors. So again, so determinant A minus Ri, and you're equating this to 0. So what is this? So this is, so the determinant will be 2 minus R, then 0, 0, 2 minus R, like this, is equal to 0. And what does this give you? It gives you 2 minus r squared is equal to 0, implying that r is equal to 2 is a double root, and or repeated eigenvalue. R is the repeated eigenvalue. So again, we find the eigenvectors. So for the eigenvectors, it's lambda minus ri x is equal to 0. So what do we get? We get, so my r is 2, so this will be 0, 0. Okay, let me write this. Not that this is wrong. Just want to say that a minus ri is equal to, so my a is 2, 0, 0, 2, like this. Then ri is going to be so minus, my r is 2, so this is 2, 0, 0, 2. So in this case, they are the same, so that when you subtract this, you get a 0 matrix, like this. So if you are solving for this in this case, what do you have? So if you're solving for this, what you're actually getting is 0, 0, 0, 0, then x1 x2 is equal to 0, 0, like this. Yes. Some people are not able to see my screen. Are there some people able to see my screen?
Yes,
It's breaking. It's breaking. We're able to see it, but it's breaking at some point. So that's the network, I think so.
Oh. Is it your network or my network?
No, I think it's just the network around Lusaka areas. Yeah, something like that. It's just the network. This is
It's his network.
It's not his network. It's the service provider's network. That's tripping, not his network. Does he have a network?
It's your network.
Okay, so you see what has happened here. Here we get the 0 matrix. Then here we have, so we want to solve this equation. So what do you think are the solutions for this equation? What should be the choices of x1 and x2? So I'm throwing that question to you. What do you think?
It has no solutions.
Really? Okay, the others?
I think we can use any number. It's like 0 to infinity. Anything.
Okay. A different answer?
I also think it's any number.
Yeah, any number is right. So what we do in this case, and in doing this example, I was saying I'm answering your question. So usually we get equations which are the same. In this case, they're also the same, only that we put 0. So this is the only different case you can get for a 2x2 case. If it's not, okay, I'll explain properly later. Let me just finish this. So what is happening here is that you have 0, x1 plus 0, x2 is equal to 0. And the second one will give you the same. So the question is, what values of x1 and x2 are going to satisfy this equation? And your answer saying any entries of x1 and x2 are correct. The only thing you want is you want linearly independent solutions. So for me, I would say there are two linearly independent solutions to this answer. And the first one is V1. I'll choose, and again, options are many. So this is just choosing. I'll choose 1, 0. And the V2, I'll choose to be 0, 1. So what has happened here is that on this matrix, we only found one eigenvalue, but to this eigenvalue, there corresponds two linearly independent eigenvectors, V1 and V2. So R is equal to 2 corresponds to these two linearly independent. By linearly independent, we mean you can't get one from the other by multiplying by a scalar. And this is a choice. It's not the only choice, but it's like the standard choice. So in this case, what we say is that so these two vectors, 1, 0 and 0, 1 are the linearly independent eigenvectors of this matrix 0, 2, 0, 2 corresponding to eigenvalue 2. So is this okay? Is this confusing?
So I just want to find out.
Yep, go ahead.
Say we had a V2 with 0 and -1 in place of 0 and 1. Does it still apply?
If you had the V2, yes, it still applies, yes. It's still fine because 0 and -1 is a multiple of this one. You can get 0 and -1 by multiplying this by -1. So yes, still apply.
Thank you.
Mm-hmm. So to explain further, this is the only other different case. And this only happens if your matrix, your given matrix is a scalar matrix. What is a scalar matrix? It's a matrix that is a multiple of the identity matrix. So in this case, this matrix is a multiple of identity matrix. I can get this matrix by multiplying the identity matrix by 2. So this is the other only different and interesting case. All the others the same. But when your matrix is a scalar matrix, that is yes, or diagonal matrix, yes.
Hello, sir. So like what if in the case where you find R is equal to 0? Like for the 12 question you gave us, we tried one of the questions that gave us like R was equal to 0. So I don't know, yes, like how do you...
There's no problem. It's the same case when R is non-zero. So when your eigenvalue is 0, then everything else, nothing is going to go wrong. So you plug it back in this equation and then you just solve. So nothing goes wrong. So it's possible, yes, for eigenvalue to be 0, and you can still solve it the same way. Have I answered?
The question was 1, 0, 0, as in the matrix was a 2 by 2. It was like 1, 1, 0, 1, as in the question. Now trying to find R, I don't know, like I can try to just work it out and see how, if you can help us.
Okay, so we go to the tutorial. So I was expecting a lot of questions on this, but it looks like I've explained it properly. No one has questions, which is good. So we move on to the...
No, sir. Sir, I've got a question.
Okay, what's the question? Before we move on to the tutorial matrix, the matrix
I
of
think
Church.
yeah, clarification. I left you when you're doing 0, 0. I got cut out by network. I didn't see how you came back to the V1 and the V2. So maybe just go through over it again. So
Yes. So what we said is that this is the equation we get, and this equation in some way is meaningless because for whatever choice of x1, in fact, in this case, what is happening is that the reason you're getting two linearly independent solutions is because x1 is not dependent on x2. Whatever I get for x1, x2 won't depend on the value of x1, or x1 won't depend on the value of x2. These two entries are linearly independent in some way. It's unlike an equation where you get x1 plus x2 is equal to 0. Here, your two variables or your two unknowns are dependent, because whatever value of x1 you fix, it should give you the value of x2. But this one is different. So that's the reason you're getting two linearly independent solutions. And I was saying, like, you can make any choices. These are the standard choices of solutions to such equations. So the first one is 0, 1. That's the standard choice. The second one is, the first one is 1, 0. Second one is 0, 1. The only thing you want to avoid to make these linearly independent is that one should not be multiple of the other. So in this case, I can't get V2 from V1. I can't multiply it by scalar and get V2. So I'm saying I can't multiply V1 by scalar and get V2. It's not possible. So these two are linearly independent, and they make proper choices. They're not the only choices. You can come up with any two vectors. The only restriction is that they're supposed to be linearly independent. Is that okay?
Yes, it's okay.
Okay. So let's do the example in the tutorial where you get a 0 eigenvalue. So can you give us, what's the matrix?
1, 1, 0, 1.
1, 1, 0, 1. Okay. So determinant of A minus Ri should be equal to 0. So this is 1 minus R, 1, 0, then 1 minus R. This.
Sorry, so it's 0, 1, 0, 0. Sorry.
0?
0, 1, 0, 1. I mean 0, 1, 0, 0. Yeah, 0
So
there. 0,
0 here.
1. Yeah.
Okay. So cancel this. So in this case, what you get is minus R, then 1, then 0, and then minus R, like this, is equal to 0. Then what is your determinant here? So minus R times minus R is R squared. Then this is minus 0 times this is 0. So yes, this is equal to 0, implying that R is equal to 0 is a repeated eigenvalue. And this is no problem. So we solve for the eigenvectors. Sorry. So we solve for the eigenvectors. Again, for eigenvectors, we're solving A minus Ri. X is equal to 0. So this becomes, so in place of R, we've got 0. So it will be 0, 1, 0, 0. Then x1, x2, is equal to 0, 0, right? So let's see what the equations give us. So this is 0, so 0, then you get x2 is equal to 0 for the first row times column. For the second row times the first column, just get 0, 0 everywhere. So this is the only equation you get. So what's the eigenvalue? Or eigenvector, sorry. What do you think? What would be your choice?
1, 0.
It would be what?
Like 1, 0, and 0, 1.
So 1, 0, and 0, 1. So you get 2. The others, what are you saying?
Sounds we're good doing the same way.
What are the others saying?
Just 1, 0.
Just 1, 0. So this one doesn't apply. So it tells you already that your eigenvectors, their second entry as 0. X2 is equal to 0. So this can't apply. So this is out. This is out. All your eigenvectors look like this. And this is the best choice. So the others are like 2, 0, 3, 0, and so on. Just work with one. So it's easier to work with
that
one.
You mean, since, excuse me.
Yes.
Sir, so you mean if x is equals to x2 is 0, you can choose any number to be x equal to 1.
Yes, exactly.
Right,
Yes, you can choose any number to be equal to x1, and it will satisfy this. The only restriction is that you can't choose x1 to be 0, because like we said, we don't want the 0 vector, because if you choose x1 to be 0, x2 is already 0, so you get the 0 vector. So in that case, you have a 0 vector, which is not allowed. But any x1 other than 0 is fine. So this is an eigenvector of this matrix, which was 0, 0, 1, 0, corresponding to eigenvalue 0.
So,
yes.
Kindly contrast this with the previous example in terms of the solutions. I think just putting them side by side.
Okay. So yes. Also, we can look at the equations, right? Where is that? Yeah, we can do this. So this is the second one, and this was so on top is the first one, and below is the second one. So for this one, what we were getting was 0, x1 plus 0, x2 is equal to 0. And this one, what we're getting is that x2 is equal to 0. You see the difference?
Yes, sir. Then in terms of our choice of solutions for the first one, we said...
Yes. So in this case, what you see is that x1 and x2 are independent. So you can choose any two vectors, provided one is not a scalar multiple of the other. And in many books, what you see is that they usually go for the standard choice. So these are the standard like vectors, and this is the standard choice. So you pick 1, 0 and 0, 1. If you picked, say, something like 1, 1 and maybe 0, 1, it's still correct. Not wrong. We just want to standardize things. Have I answered your question?
Yeah, I wanted to find out, would picking, let's say, 1, 1 and 1, 1 be correct in the first instance?
You pick 1, 1 and?
1, 1.
They are the same. They are the same, actually. So it won't be correct. If you pick 1, 1, It wouldn't be correct. If you pick 1, 1 and 2, 2, it also wouldn't be correct because this is a scalar multiple of this one. When I multiply 2 by this one, I get this one. So these two vectors are actually dependent. They're not independent. So this choice also wouldn't be correct. If I pick 1, 1 and, for example, 2, 3, correct. So this is correct.
I see.
Not correct.
Thank you, sir.
Okay.
But a quick question.
Yes.
For the conditions that you've given us, isn't the last equation independent? Isn't x1 independent of x2 since x2 is equal to 0? You can bring the last page.
Okay, so where are we? Oh, this one.
Yes. So x2 and x1 are independent of each other. So doesn't that bring us to the solution that we had for the previous example? She said if they're independent of each other, then you should have, is it 2 distinct solutions? Something like that. Maybe I didn't get it right. But that's what she said, something like that.
I get your point, but they're different, right?
So this is an exception?
No, not really an exception. The only problem with this one is, yeah, you can argue that x1 and x2 are dependent, but the vectors won't be independent. The vectors will be the same. So all the vectors of this form x1 and x2, which have got entry 0, will be dependent because you can easily multiply one and get the other by a scale.
Oh, so the dependency only acts on the vector and not x1 and x2.
Yes, not on the variable.
Not on the variables. Okay.
Yeah, on the vectors, yes. Do we have any more questions? So once you understand these eigenvalues and eigenvectors, the solving part of these systems of equations will be easy. The tricky part is to understand eigenvalues and eigenvectors. So can we move on?
Yes.
Okay. So there are 2 examples we're remaining with, which are lined up. One is complex, the other is a 3 by 3. I think let's do both. And we'll try to do as quickly as possible. So have this. You have to find again, task is eigenvalues, eigenvectors. So go straight, or let me just write down its determinant of a minus ri is equal to 0. So this is minus 4 minus r, then negative 17, 2, then 2 minus r is equal to 0. So the determinant of this is minus 4 minus r, in brackets 2 minus r, then plus 34 is equal to 0. Opening the brackets, we have minus 8, then plus 4r, then minus 2r, plus r squared, plus 34 is equal to 0. Collecting the like terms, you have r squared, then this is minus 2r, and then 26, yes.
Plus 2r, I think.
Yes, plus 2r, thank you. Plus 2r plus 26 is 0. So you can try to analyze this. Can you factorize this? If you can't, or if you want to go the easier way without any thinking, you can do the quadratic formula. So this is R is equal to minus B. So B is 2, so this will be minus 2, then plus or minus the square root of B squared. So it will be 4 minus 4. What is my A? 1, and my C is 26 over 2A. So over 2. So what does this give you? So it's minus 2 plus or minus. What do we get there? So it's 4. Then this is 4 multiplied by 26, which gives us what? Which gives us 104. Yes. So it's minus 104 over 2. So this is minus 2 plus or minus. So 4 minus 104 is negative 100 over 2. So this is negative 2 plus or minus. So this will be complex now. So this will be I and the square root of 100 over 2 minus 2 plus or minus. The square root of 100 is 10. So this will be 10I over 2. So what you get is minus 1. If you divide by 2, it's minus 1 plus or minus 5I. So you've got two eigenvalues. First one is minus 1 minus 5I. And the second one is minus 1 plus 5I. So in the case of complex, where eigenvalues are complex, it means that one is the complex conjugate of the other because of this quadratic formula thing. So these are eigenvalues. Let's find the eigenvectors. So we start with R1. So we want to find eigenvectors corresponding to this eigenvalue. So we go back to this. This is the equation we go back to, and this will give us, so it's minus, yes. So this will give us minus 4, then minus, so this is my R, so it's minus 1 minus 5I, and this is minus 10. Then this is 2 minus 2 minus then 1 minus 1 minus 5I. So this is the minus Ri. Then you want to find x1, x2 is equal to 0, 0, like this. Okay, so so this will become so it's minus 4, so this will become plus 1, so it's 5, right? No, 3. So this will be minus 3, then plus 5I, and this is minus 17, then this is 2, then this is 3 plus 5I. X1, X2, equal to 0, 0, 0. So if we multiply this, we have minus 3 plus 5i, x1 minus 17, x2 is equal to 0. The second equation is 2x1 and plus 3 plus 5i, x2 is equal to 0. So these are our two equations, and these equations must be the same. Can we verify this? How can we verify this? Should we do this, or should I just pick on one? Do I need to verify that one is a multiple of the other?
Let's verify some.
Yes, just verify.
Okay, so what do I do here? Okay, so let's do this. This one. So this second equation, 2x1 plus 3 plus 5i, x2 is equal to 0. We divide this by 2. So divide by 2 everywhere. So we have x1 plus 3 plus 5i over 2, x2 is equal to 0. And then we multiply this equation by minus 3 plus 5i. So what it gives us. So multiplying by x1, I get minus 3 plus 5i, x1, then plus minus 3 plus 5i, then 3 plus 5i over 2, x2 is equal to 0. So this is minus 3 plus 5i, x1. So we open the brackets here. So it's negative 3 times 3. That will be minus 9. Negative 3 times 5i, that will be negative 15i. Then 5i times 3, that will be positive 15i. Then 5i times 5i will give us what? It will give us negative 25, right? Yes, negative 25 over 2. So this is x2 is equal to 0. So this will be minus 3 plus 5i, x1. What does this give me? These cancel, so these cancel. Then 15, negative 9 minus 15, that's negative 34 over 2, x2 is equal to 0. And this gives us the first equation, which is minus 3 plus 5i, x1, so negative 34 divided by 2 is negative 17, x2 is equal to 0, which is the first equation. This one, yes. So you see that you can get equation 1 out of equation 2 by multiplying it by, in this case, we divided by 2, then multiplying it by negative 3 plus 5i. So verified. Are we happy?
Yes.
Okay. So we can just work with one equation, and usually in your assignments or your exam, you don't need to verify. So for the 2x2 case, we say the only case where things can be possibly different is when you have a scalar matrix, like the one we have at 2, 0, 0, 2. Otherwise, everything else, you're going to have this situation where equation 1 and equation 2 are the same. So you don't need to verify, you don't need to waste any time. So we'll just work with this one, the equation 1. What do we get? So we can say my x1 is, I can choose my x1 to be 17. And if I choose my x1 to be 17, then my x2 has to be -3 plus 5i. So I've just swapped them. There's a minus here, so this will give me 0, I'm assured. So if that is my case, it means that x1, x2 is equal to, so x1 is 17, and x2 is -3 plus 5i. And this is your eigenvector. And since it has got complex entries, if you want, you can write it in the form a plus bi, where you have the real part and the imaginary part. So in this case, so this 17 -3 plus 5i, writing it in the standard form, you're going to have 17 here, -3 there, then plus I, then 0 there, and 5 there. So this is the form A. In this case, they are vectors plus bi. So this is the eigenvector of the given matrix, so of A corresponding to eigenvalue. So what was the eigenvalue? It was -1 minus 5i.
So,
yes.
I have a question concerning the thing. So is it possible to solve, like in the case of this complex one, using row reduction method?
Yes. Yes. Which second one are you talking about? As in this specific example?
Yeah, but like given a scenario of a complex number kind of solutions. So like, would it be possible to use a row reduction method on it effectively?
Yeah. So have you done row reduction?
Not typically. No, I wouldn't say so, not very much.
So what you're doing in row reduction is that you're trying to like simplify your two equations. So if these are your two equations, you're trying to simplify them or bring them down. But in this case, the row reduction won't be helpful because they are the same. These two equations are the same. So what you're going to get is 0, 0 everywhere. If you multiply, if you say subtract equation this by this, you're going to be getting the same entries because these two equations are the same. So instead of using the row reduction thing, we just work with one equation and then get our solution from there. So if that answer is not helpful, I'd say row reduction is particularly useful when you go to higher matrices like 3x3 and 4x4, where you've got a lot of equations. But for the 2x2, I would say you don't need it. You don't need to have the knowledge of row reduction. Is that okay?
Okay, sir. Yes, that's fine, sir.
Sir, so on this one, we don't need to find the eigenvectors of the R2, the -1 plus 5i. We don't need to do that one. Eh?
we need to, yes, we need, only that it's a lot of work. But the other thing, so when it's complex, things become a little bit nice. So what you have is that complex values, your eigen, so you had R1, so we found -1 -5i, and your R2 was -1 + 5i. So you see that R1 is complex conjugate of R2, and it's also going to apply for the eigenvectors. So it reduces our work. So if this is, so the vector is 17 - 3 plus I 0, 5. So this is the eigenvector for this one. The eigenvector for this one, R2, is going to be 17 - 3 minus I 0, 5. Yeah. So eigenvectors are complex conjugate, and eigenvalues are also complex conjugate for the complex case. So that's like proven, it's a theory. And so you can just go ahead and use it. If you want, you can verify that indeed you're going to get the same thing. Have I answered your question?
Yes, you have. Thank you.
Do you have any more questions? So I had also lined up a 3x3 matrix. Should we do it?
Yes.
Yes.
Yes, sir.
Yes. Let's do it.
Yes, sir.
Okay. Just give me just trying to connect my gadget to the charger. Just need a few seconds. Okay, so we do the 3x3. Okay. So the 3x3 is a little bit involving. There's a lot of entries, but the theory remains the same. So this is our 3x3, 0, 1, 1. Then you have 1, 0, 1, 1, 1, 0. 3x3 matrix. So again, you want to find the determinant of A minus Ri is equal to 0. This is your characteristic equation from which you find your eigenvalues. So this will become minus R 1, 1, 1 minus R 1 and 1, 1 minus R. So I want to find the determinant of this and equate it to 0. So I'm assuming you know how to find the determinant of 3x3 matrix. Do you?
Yes.
Okay.
No.
Good.
We don't.
Okay.
We don't.
You didn't do this in second or first year?
We forgot.
Okay, let me remind you. So we're going to use, there are a lot of ways. You can use any row or any column. We're going to use the first row. So using the first row, the first entry is minus R. Then we find the determinant. So if we remove this, we remain with this of this 2 by 2. So it's minus R, 1, 1 minus R, like this. Next one is this entry, and this entry becomes negative, so it's minus 1. Then, so this is the entry, remove these, so you have 1, 1, 1 minus R. This, the last entry in this row is 1, and this is plus 1. And then remain with this matrix. So it's 1, 1 minus R, 1, like this. So simplifying, this is minus R. Then this will be, so this is just 2 by 2. So it's R squared minus 1 minus, this will be 1 times minus R is minus R. So it will be minus R minus 1 again. Then plus, so this will be 1 plus R, like this. Yes. And so this is opening the bracket, have minus R3, then plus R, then plus R, plus 1, then plus 1 plus R.
So why is it that at the top we put minus 1?
Why is it that?
That we did minus 1 instead of plus 1.
Where, on the second entry?
Yes.
Yeah, it's how you define the determinant for a 3 by 3.
Okay. All right. No, okay.
Yes. So this will be minus R3. How many R's do we have? We have 3, so it's plus 3R. How many ones do we have? 2. So now this is a cubic polynomial. We have to find its roots. And what can we do? Any suggestions on how we can find the roots here?
Synthetic division.
Synthetic, but what are we dividing by? Which polynomial are we dividing by?
You find the zeros of the polynomial.
We find the zeros. Yeah.
Divide.
The zeros, it's trial and error, right? So I think you have to look at the multiples of this. So let's try 2.
So I tried -1 and it worked. -1. This is R plus
-1.
Yeah.
So let me just try it. So this is minus, then -1 cubed, then plus 3, -1 plus 2. So this gives me, so this is -1 to the 3 is negative. So this is 1 minus 3 plus 2 is equal to 0. So it works, yes. So -1 is the root, meaning R plus 1 is the root of this. So R plus 1 is a root of this polynomial, and we can divide this. So I always forget synthetic. I usually use long division. So long division, R into this is minus R squared. Then this multiplying like this, you get minus R cubed. Okay, just give me a few minutes. Okay, so this is long division. Then minus R squared times 1 is minus R squared. Do the subtraction. This and this gives us 0. this is going to give us r squared plus 3r plus 2. Repeat the process. R into this is plus r. And then r times this is r squared, then plus r. Subtract. R minus r squared is 0. 3r minus r is 2r, so plus 2. This into this is 2. 2 times r is 2r plus 2, so we get 0. So what this means is that minus r3 plus 3r plus 2 is, this is a factor, so it's r plus 1. And then this is the quotient, so it's minus r squared plus r plus 2. Okay, then I think we put the quadratic there, so we can try to factorize. So can we factorize this? Yes. So r cubed plus 3r plus 2 is equal to r plus 1. Then this will be, what would it be? Can somebody help?
That's r minus 2. No, r plus 2 and r minus 1.
So you said what?
The factors will be r minus 2.
The factors at 1 negative 1.
So r minus 2 and minus r minus 1, I think, yes. So this is minus, yes, r plus 1 squared and then r minus 2. Yes. So if you equate this to 0, you get ri is equal to negative 1 or ri is equal to 2 as your eigenvalues. Okay, that was long but worth it, I think. Now let's find the eigenvectors. So this is where it can be interesting. So we want to find eigenvectors first corresponding to r is equal to negative 1. So what are we solving? It's r a minus ri x is equal to 0. So yes.
And it's supposed to find 3 errors.
Why do you say that?
Because it's a 3 by 3 matrix.
Yes, sometimes you can find 3, sometimes you can find 2, sometimes you can find 1. Possible. Okay. Just like in the 2 by 2 case, there are cases where we're just finding one eigenvalue. So in this case, we've got r is equal to negative 1, which is because it has got multiplicity 2, or it's a double root because of this squared. So it's still fine. Are you happy?
Yes, I am.
Okay. So when you replace negative 1 in this, what you get is 1, 1, 1, 1, 1, 1, 1, 1, 1, like this. Then x1, x2, x3, because this is a 3 by 3. Then you have 0, 0, 0. Yes. And so what you see is that when you multiply everything, all the 3 equations are going to be x1 plus x2 plus x3 is equal to 0. So you just choose one of them, just work with one. They are going to be the same. So what do you think now are the solutions to this equation? So what do you think? Anyone? So in this case, what we are going to get are two linearly independent eigenvectors. And how do I know? Because from this, I know that I need to fix two possible values to get the third one. If I fix 1 and 2, I know I'll be able to get x3. So what is happening is like this x3 is dependent on what x1 and x2 are. So what I do using previous knowledge and standardizing is I'll say we get 2. So we get to v1 and v2. So for my v1, I'll let x1 be equal to 1 and x2 be equal to 0. So this was the trick we used in the 2x2 case. And for my v2, I'll let x1 be equal to 0 and x2 be equal to 1. So I don't want v1 to be a multiple of v2, a scalar multiple of v2. And so you can write it out now. So x1 is 1, x2 is 0. So if I fix this, what would be my x3?
-1.
-1. Yes. For my v2, x1 is 0, x2 is 1. What will be my x3?
-1 as well.
-1 as well. And so these two are my eigenvectors. So I've got two linearly independent eigenvectors corresponding to this single eigenvalue r is equal to -1. Is this complicated, or are you starting to get the idea at least?
Somehow it is complicated, but
yeah, so this is how you do it. So this choice of 1 and 0, again, like I always keep emphasizing, it's not the only choice. It's the standard choice, and what you're trying to do is you're trying to avoid one being a scalar of the other, because if it's a scalar multiple of the other, then they're dependent in some way. Okay, so this is for R1. Let's find for R is equal to 2, the other eigenvalue. So for the other eigenvalue, R is equal to 2. So again, you're solving A minus Ri and X is equal to 0. So what does this become? So in place of R, you put 2. So it will be minus 2, 1, 1, then 1, minus 2, 1, 1, 1, minus 2, x1, x2, x3 is equal to 0, 0, 0. And so from this, what you get 3 equations. So you have minus 2, x1 plus x2 plus x3 is equal to 0. The other one is x1 minus 2x2 plus x3 is equal to 0. Then x1 plus x2 minus 2x3 is equal to 0. Okay, so here are your equations. And how do you find what your x1 and x2 should, x1, x2, and x2 should be? So there was talk of row reduction. We can use that. But since you haven't done row reduction from second year, we can still use the amateur way of doing this. So what you do is, let's pick on one equation and then plug it in the others. So if we pick on equation 1, so if you pick on equation 1 and we make x3 the subject, so it will mean x3 is going to be 2x1 minus x2, like this, right? Then I plug this into equation 2 and 3. So plugging it in equation 2, I have x1 minus 2x2. Then this is my x3, so plus 2x1 minus x2 is equal to 0. And simplifying, I get 3x1 because it's x1 plus x2. And then this one gives me minus 3x2 is equal to 0. Then how about equation 2? So for equation 2, so this is equation 1. I plug it in equation 2. So I want to get this equation 1 now, plug it in equation 3. So I'll have x1 plus x2. So this is my equation 3. Then minus 2, plug in equation 1. So it's 2x1 minus x2 is equal to 0. So this is x1 plus x2. Then this is minus 4x1 minus 2 plus 2, sorry. x2 is equal to 0. Collecting the like terms, I get minus 3x1. So this is x1 minus 4x1 gives me minus 3x1. Then x2 plus 2x2 gives me plus 3x2 is equal to 0. So if you compare these equations, they're actually the same. If you multiply this one by -1, you get back this one. So again, you can just work with one. So let's work with this one. Let's work with 3x1 minus 3x2 is equal to 0. So you see here that if we get x1, fix x1. If we get x1 to be 1, then x2 is going to be 1. And what will be your x3? You go back to what you made. So x3 is equal to 2x1 minus x2. So x3 is going to be 2, x1 is 1, x2 is 1, so x3 is 1 also. So all your entries are 1. So you get that this vector 1, 1, 1 is an eigenvector of A corresponding to eigenvalue R is equal to 2. Is this okay?
Yes.
Yes.
Do we have any questions? So the higher you go, again, the more complicated it becomes and the more involving it becomes. So usually we just give you 2 by 2. The purpose of giving you 3 by 3 is to just open up your minds to other possibilities. So a lot of things it's possible you can just get one eigenvalue, which corresponds to 3 linearly independent eigenvalues, and so on.
So in these cases for 3x3 matrices,
yes,
can you be given an equation whereby one of the roots is a double, then another one of the roots is complex? Or say one of the roots is complex and the other root is just the normal root.
Yes, it is possible. Yes. It is possible. So it's possible you have your characteristic equation gives you one root which is real, and the other roots which are complex. The other 2 roots are complex, and because they are complex, they're going to be conjugate to each other. Yes, so it's possible. So if they are complex, then there must be, you can't have only one complex and 2 real roots. No, it has to be 2 complex and 1 root. Because the equation you're starting with, characteristic equation, has real coefficients. So it has to have 2 complex and 1 real.
All right, so are we to expect any questions of that format? And do they have a different type of way of solving them as compared to the last complex one that we solved?
No, same method. Find your eigenvalue, then replace in that equation to get your eigenvector. So nothing different, just the same. So should we end here?
Yes.
Yes.
Let's end there.
Okay, so the recording is going to be available after this, and this marks the end of eigenvalues and eigenvectors. Next class, we solve systems of first order linear differential equations, and that will be, since we've done this background, that won't take much time. So see you next time.
All right.
Thank you. Good day, everyone.
All right. Thank you.